Hey guys, welcome to the second video in the series looking at two-dimensional motion. We started off the series looking at the equations of uniformly accelerated motion and kind of just arrived where these equations come from. This second video looks at specifically projectile motion and what equations we can kind of use to describe what happens to an object when it tends to become a projectile. So there are two things that we'll typically look at. One of them is the velocity, right, of the specific projectile, and the other one is the position of the projectile. Remember that but that velocity is defined as a vector quantity, which implies that it has both magnitude as well as direction. Now, velocity is not the only vector quantity. It includes things such as acceleration. Acceleration is also a vector quantity. Things like force and displacement are all examples of vector quantities, because by definition a vector has magnitude and direction. So in this instance, let's pretend that I have a ball and you got some, let's say like a soccer player, and he's coming to kick the ball. So he's busy running up and gives the ball a good kick, and the ball will leave with some kind of velocity, right, which we'll call just v sub naught, just indicating that it's the initial velocity. And then once the object is in the air, it will be subject to the laws of physics, and we know that the moment that it tends to leave the ground with that velocity, it will follow this kind of parabolic path and will land at some instant on the ground some time later, some distance from where it was released. Okay. So part of what we'll do is subdivide everything into x and y components. Remember, as the ball is at any point in time here, it will have some x and y position, right? It will have some x and y position here, some x and y position here, some x, y position here. So the x and y coordinates will represent where it is at any point in time. So I can subdivide its path into x and y positions, but also this velocity vector. Remember that it has both magnitude and direction. The direction of this velocity vector is defined by this angle theta with the horizontal. But in essence, it means that I can break this velocity into a horizontal component, which we'll call v sub naught x to indicate the initial velocity in the x direction. And we'll also have some components in the y direction, which we'll call v sub naught y, to denote the component of the initial velocity going in the y direction. So v sub naught x will be defined as v sub naught cosine of the angle, and v sub naught y can be calculated as v sub naught sine of the angle. And you might be asking, well, where on earth do I get this from? Remember, these are magnitudes, so in essence it's describing the size of the initial velocity in the x direction and the size of the initial velocity in the y direction, which we can calculate by this specific formula. Remember that if we have this kind of triangle, this not equilateral triangle, this right angle triangle, we can use Pythagoras to calculate what the size is of each of these sides of a triangle. I could use the same principles whether this unit is velocity, acceleration, force, displacement, whatever the case may be. I would go about solving this the same way. In this case, it just happens to be velocity. So if you guys remember that the cosine of any angle is defined as the ratio of the adjacent divided by the hypotenuse. Okay, well, on a triangle, this is the adjacent side, because if this is the angle of interest, then this is next to the angle, and the longest side is always the hypotenuse. So if I simply replace the labels that I have for this specific triangle in this case, the adjacent is simply v sub naught x, and the hypotenuse is just simply v sub naught, just the initial velocity. So if I then multiply this out to that side, then this would become v sub naught cosine of theta is equal to v sub naught x, which is kind of what we have here, right? You might also remember that the sine of any specific angle, so the sine of some angle is defined as the opposite side, or the ratio of the opposite side divided by the hypotenuse. So in the same right angle triangle, remember that the side opposite the angle is just defined as the opposite, and that's still our hypotenuse. So if I again replace the labels, this would just be v sub naught y, and this would be v sub naught. Again, I would multiply that out. This would become v sub naught, the sine of whatever the angle is, gives me this v sub naught y. And again, that's what we have over here. So that's just kind of where it comes from, right? So it's saying that I can calculate the component of this initial velocity that's causing the ball to move forward by using this v sub naught cosine theta, and I can also calculate the component of this velocity that's causing the ball to move in an upwards direction by using this v sub naught sine of theta. Okay, it's going to tell me how much velocity is responsible for making the ball go up and how much velocity is responsible for making the ball go forward. Okay, so a key concept here, really important with projectile motion, is that you can treat x and y components separately. Okay, so we'll come back to this in a second, but this is kind of where like those equations of uniformly accelerated motion become really important. Okay, so the equations, remember, like I was saying earlier, is that the velocity and position when we are investigating projectile motion are really important. So the equation that pertains to uniformly accelerated motion for velocities was one that we derived earlier, which just says the final velocity is equal to the initial velocity plus the acceleration times some change in time, right? So this one's going to become really fundamental. We're going to divide this into x and y components. In terms of position, we had a equation that we could use to define the position at any point in time. It in essence says that the final position is equal to the initial position plus the initial velocity times the change in time plus 1/2 the acceleration times the change in time squared. Again, we will subdivide this into x and y components when we are analyzing this projectile motion. Okay, so how do we go about doing all of this? What I would do is kind of create these big labels around x calculations and y calculations, and make sure that we are keeping everything nice and separate. I'm just going to put this wall here. So we'll start off with the x side. So I will use this equation of uniformly accelerated motion, but for every value that I put in, I will only use the x components of it. So it'll look something like this. In essence, it'll say that the final velocity in the x direction is equal to the initial velocity in the x direction, or in this case we used initial velocity, we use that v sub naught plus the acceleration in the x direction times this change in time. Okay, so when we're dealing with projectile motion, it in essence means that this object is in the air for some period of time, right? So when it's left the soccer player's boot and it's at this point or any point along this path, the only forces acting on it would be the force of gravity, right? The force of gravity would be pulling this down. And you might say, okay, well, there's also maybe some wind resistance that might be slowing the path of the ball. And you would be entirely correct in saying that. But in order to keep things simple, we'll say that we will ignore wind resistance for now. Okay. So in essence, the only force acting on this object through its full flight path is just the force of gravity. So there's no wind resistance, which means that any acceleration or deceleration in the x direction or horizontal direction is going to be 0. Okay, so we'll ignore anything like wind resistance, or wind drag, or anything like that. So in essence, this whole formula over here, where we're putting in all these x values, this, if acceleration in the x direction is 0, then this whole thing becomes 0, which in essence means that the final velocity, which I just simplify as Vx, is simply going to be, well, some velocity at the end is just going to be equal to the initial velocity in the x direction. But remember, the initial velocity in the x direction, we said, is defined as this initial velocity in the x direction is v sub naught cosine. So this just becomes v sub naught the cosine of that angle. Okay, and it's unchanged. It means velocity at the end is going to be equal to whatever the horizontal velocity was in the beginning. Alright, let's do the same thing for position. So the position, the final position in the x direction is equal to the initial position, or just x sub naught, in the x direction, plus v sub naught x times this change in time, plus 1/2 a x times change in time squared. Okay, so we've already agreed that a acceleration in the x direction is going to be 0, so all of this tends to go to 0 again as well. So it says that the final position is equal to the initial position plus v sub naught x delta t. Okay, and we've seen in a previous video that this aspect here simply explains how much further an object goes when acceleration is 0. Okay, v sub naught x we already identified here as being v sub naught cosine of theta, so the final position in the x direction is equal to the initial position plus v sub naught cosine of theta times the change in time. Okay, so this is one really important equation that applies to projectile motion, and this is the other one. So one describes its velocity at any point in time. So let's make that a bit of a nicer line. One describes its velocity at any point in time, and the other one describes its position, its horizontal position at any point in time. We will do the same thing for basically the velocity and position in the y direction. So in terms of the final position in the y direction, it's equal, final velocity in the y direction is equal to the initial velocity in the y direction plus the acceleration in the y direction times the change in time. Now, acceleration in the y direction is simply gravity. The reason it's negative is because it's acting down, and our conventional setup is anything that's acting to the left, to the right and up would be defined as positive. Therefore, anything going down to the left would be defined as negative. Okay, and we also found earlier that v sub naught y is equal to this v sub naught sine of theta, right? It's defining the vertical velocity. So the final velocity of a projectile is equal to its initial velocity, which is v sub naught sine of theta, right? Plus this acceleration in the y direction, which is just negative g times the change in time. So the final velocity in the y direction is equal to v sub naught sine of theta minus g delta t. Okay. What's really interesting about this is that we have some kind of initial vertical velocity, and for every single unit of time that passes, this velocity, this initial velocity, will decrease by some magnitude of gravitational force acting on it during that time. So when it's undergoing this flight path, right, the vertical velocity that this object experiences initially will be quite large, right? But now when it's over here, some point in time later, in other words this delta t, gravity will be pulling on the object down. So this initial velocity is going to decrease by that amount, and you'll find that its velocity at any point in time starts becoming smaller and smaller and smaller, and eventually will be 0. And then gravity is still pulling it down, so it's going to start accelerating down in the downwards direction, right? It's being pulled back down towards Earth, and therefore its speed at any point in time will increase faster and faster and faster. Think about a skydiver, right? The skydiver kind of starts in this position on a plane, jumps out, and then is just constantly being pulled down by gravity. Okay, so same thing happens with projectile motion. Okay, so this is a really fundamentally important equation. So I'll just box that to make sure that we remember that. Okay, what about its position? So its final y position is going to be equal to its initial y position plus its initial velocity in the y direction times some change in time plus 1/2 acceleration in the y direction times change in time squared. Okay, so this time acceleration in the y direction, unlike acceleration in the x direction, is still negative g. So this becomes position in the y direction plus v sub naught y, we said was this v sub naught sine theta, so we'll just replace that in there, times this change in time. Acceleration in the y direction is minus g, so we could write this, let me just write it out in full, minus g times change in time squared, but a plus times a minus just becomes a minus, so this final position is equal to the initial position plus v sub naught sine of theta times the change in time minus 1/2 gt g change in time squared. Yeah, so it looks a little bit more complicated than the x direction, but once you isolate the values, it's really not that bad. Okay, because we kind of highlighted where each of these come from. We've highlighted where the formula comes from, but there's some key aspects in all of this. Notice how in these formulas over here there are no y's, right? There are no y's in this formula, and on this side there are no x's, right? So whatever values I plug in here are completely dependent on the y variables, and whatever values I plug in here are completely dependent on the x variables. So they can be treated completely independently. Okay, so really important concepts to take into consideration, and these are your two fundamental formulas that allow you to solve a whole bunch of things. So you'll be able to solve for the complete time of flight of a projectile. You'll be able to solve for range as in how far the projectile travels, you'll be able to solve for height. In other words, what is the height that a projectile will ultimately reach? And it will give us some really important insights into what tends to happen with projectile motion. I'll show in a subsequent video exactly how this tends to apply. So what are the variables that tend to govern projectile flight, and how do we go about calculating various aspects. Okay, so I hope that's given you guys some kind of insights into what projectile motion is all about, and the formulas that can be used to govern it. Again, it's really two straightforward, simple formulas that look somewhat complicated, but remember that they're all based on those fundamental two equations that we spoke about a little bit earlier here. That velocity is governed by this equations of uniformly accelerated motion, right, which was described in an earlier video, and position. Again, what is the position at any point in time of the projectile? And each of these are independent in terms of their x and y components. Okay, so we can analyze them and assess them separately, and then kind of put them together at the end to describe what happens in this projectile motion at any point in time. Great, so I'll end it here, and in the next couple of videos we'll go through some concept tests. We'll put a couple of sample questions together, so it allows you some time to go through it, work your way through it, and kind of compare your answers and see if it starts making sense. Okay, I'll leave it there for now. Good job. Thanks guys. Bye.